Algorithms. Okay, so we're going to talk about polynomial functions. So a polynomial is a function of the form this, an x to the n minus 1, x to the n minus 1. So these, the a's are coefficients. Usually you even specify that they're real numbers. And then the n's are whole number powers. So that's what polynomials are. So stuff like p of x equals 2x squared plus x plus 3, that's a polynomial, right? That's specifically a quadratic polynomial. Technically, p of x equals x plus 3 is also a polynomial. Is stuff like root x plus 3 a polynomial? No. So you have to, the only rule is that you have to have whole number, positive number powers. Okay, that's all. Would 1 over x plus 7x plus 2 be a polynomial? No. So there's no x's in denominators. So it's just numbers to positive powers.
So if it was 1/3 x plus 7x plus 2 would be?
1/3 x plus 7x plus 2, yes, we'll even say squared there, yes. So your coefficients can be fractions. That's okay. They could even, if you want to be really crazy, pi x cubed. Oh.
And same thing with square roots too, as long as the x is not in the square root.
Yeah, you just cannot have x's. Yes, exactly. It's a great question. If you say had like square root 2x cubed, that's totally okay. Does that make sense?
Yeah.
Yeah, that's what you're asking. Yep. So your coefficients can be irrational numbers, that's totally fine, but your variables have to be raised to whole number powers. That's the only rule. Okay, so the first thing is a definition of what's meant by a zero or a root. A number r is said to be a zero or a root of a function. So what do you think? A number is a zero if you plug that number in and you get out 0. Most mathematical definitions make sense, right? And the real number zeros, so this is like saying you solve the equation 0 equals p of x, right? So sometimes those zeros are going to be real numbers, sometimes they're going to be imaginary numbers. If they're real numbers, what do they correspond to of the function or the graph? They're the x-intercepts, exactly. If they're real numbers, we're not going to graph any imaginary x-intercepts. Okay? So one of the things I do care that you can do is find zeros of a function, and to make it easier, it's going to be often given in somewhat factored form. So we want to find the zeros. So set this thing equal to 0. Yeah. And solve like crazy. Yes?
Will there ever, well, obviously not in our math, but will there ever be a way to graph imaginary numbers?
You can graph a single imaginary number, like 1, by using one part of the plane as the real part and one plane as the imaginary part. When you do ordered pairs, you would need 4 dimensions. So no.
This sounds fun.
Moving on. Okay. For everybody else who doesn't want to think about that 8 in the morning. So first set x minus 4 equal to 0. What number comes out then?
4.
X equals 4. So that's 1, 0. When you set x plus 7 cubed equal to 0, does the fact that it's cubed actually really matter at all? No, you'd cube root both sides and the cube root of 0 is still 0, right? So you're going to get x plus 7 equals 0, so your x value is? -7. Okay. And if you can find those by looking at the polynomial, you can just tell me what they are, okay? Because it's like so easy. The next one, you're allowed to just write down what they are if you're accurate. X squared plus 9 equals 0. Does that factor? No. X plus 3, x minus 3 if it's x squared minus 9. So this is the same thing as x squared equals -9, right? So what are the two answers for that?
Plus or minus 3i.
X equals plus or minus 3i. Okay, so you've taken care of the first factor, the second factor, the third factor. Now the fourth factor, x squared minus 2x plus 2 equals 0. Does that factor? Does not. So you can use the quadratic formula or you can complete the square. In this case, I think completing the square actually isn't that bad. So x squared minus 2x would equal negative 2. What number do I add in here to complete the square?
1.
1. So plus 1 on this side, plus 1 on this side. So that's x minus 1 squared equals negative 1. X minus 1 equals plus or minus the square root of negative 1, which is just I. So x equals 1 plus or minus I. Okay, so holy moly. If you don't like completing the square or you slightly forget how to do it, what is the quadratic formula you would use? X equals, tell me the formula, not what you get when you plug stuff in. Tell me the general formula, not what you get when you plug stuff in.
Minus b plus or minus the square root of b squared minus 4ac
Over
2a.
2a, there you go. Okay, so if you don't like completing the square, that's the other option if you can't factor. Which ones are x-intercepts? All the ones that are not I. Does that make sense? So all the ones, there's x-intercepts at x equals 4 and x equals, what else? -7. I think that's it, right? There's no other ones that are x-intercepts? Okay, how about you try the next one, because it's like the exact same thing, I just changed some numbers around. There's even a complete the square part. You all right?
Is it B for the
Say that again?
Is the next one already B?
The next one that we're doing is part B, yes. That one. What's one intercept?
-5.
Or 1, 0. X equals -5. That came from this factor, right? Okay, how about when you saw x squared minus 4 equal to 0? Does that one factor?
Yes.
Does the fact that it's squared matter at all?
Yes.
So this whole thing squared. First, I would square root both sides. I don't think it matters that it's squared.
The x squared that matters.
Oh, I see what you're saying. Yep, there were two squares. I didn't specify. That factors into x plus 2, x minus 2. So what are your two answers there?
Plus or minus 2.
X equals plus or minus 2. You could have also solved that by moving the 4 over and square rooting, right? Same thing. Okay, how about the x squared plus 4 equals 0? First thing?
Move it over.
Don't forget your plus minus, and you get 2i. And the last one, completing the square, I think works out pretty nicely. So how am I determining that completing the square works out nicely? Like why do I say that?
2 divided by 1 squared is a nice number.
So yeah, so when you complete the square, you have to half this and then square it, right? And if you half that number and you get a whole number, as in not a fraction, then it's not that bad to complete the square. That's how I would say you'd check. So x squared plus 2x equals -5. What number do you add in?
Plus 1.
Plus 1. Okay, so how does that factor then?
X plus 1 squared
Great.
equals -4.
And then square root, you get x plus 1 equals plus or minus
2i.
2i, and your final answer is x equals,
Plus or minus.
mm-hmm,
That's a nice job.
It doesn't actually matter who's first, so like Cole, you were gonna say plus or minus 2, I minus 1 is the same thing.
Yeah.
Okay, of these values, which ones are the x-intercepts?
Anything without an I.
Mm-hmm. Yep, x equals -5, +2, -2. So that graph of, if I were to graph that function, it would cross the x-axis 3 times. Yes?
So if there was a double root in one of these, would we have to specify that or not?
We're going to get to that in a second. So like it definitely is the case that 2 and -2 are roots of multiplicity 2, and we're going to specify that later on. Yep, exactly. Okay, so here are properties of polynomials. So let's think about the polynomials that you have actually seen pictures of. So you have seen things like y equals mx plus b. In general, they look something like this or the other direction, right? You've also seen ax squared plus bx plus c. What is their general shape? U, exactly. Okay. So if you have a polynomial, all you're doing is plugging numbers in and raising them to whole number powers, right? Is that ever going to do anything mathematically illegal, so to speak? No, it never will. So this says, the first thing is that the function will be defined for all real numbers. That's like saying the domain is always going to be all real numbers for any polynomial. There's no square roots, there's no fractions that have x's in the denominators. So all real numbers. The second property is they're not going to have any sharp corners. So if there's a turnaround point, it's always going to be kind of like a smooth thing. Can you think of a function that has a sharp corner that you know a picture of?
Absolute value.
An absolute value does. That has a sharp corner. Okay, so an absolute value is not a polynomial. Okay, now the second thing. So when you have a line, how many zeros is that going to have? It's just going to have 1. It's going to cross the x-axis once at most. Always once, actually. When you have a quadratic, it crosses the x-axis 2 times for that. Do all quadratics have to cross the x-axis?
No.
You could have one up here, right? It doesn't cross at all. But the general rule is it has at most n zeros, where n is this thing called the degree, and the degree is the highest power. So if you have degree 2, you cross the x-axis at most twice. And at most means you could cross less than twice, that's also fine. Okay, so how many turning points? Does a line have any turning points where it changes direction? No. Does a parabola have a turning point?
Yes.
Yes. So if the degree is equal to 2, you have 1 point of turning. If the degree is equal to 1, you have 0 points of turning. You see how it's always 1 less? And it does say at most because sometimes there aren't, like that's just like the maximum number. There might be less.
So sine wave has a degree of infinity.
A sine is not a polynomial.
Okay.
Yep. And the reason is it has an infinite number of turning points. And the other thing is that it increases or decreases without bound. So it just goes up forever and ever or down forever and ever as x goes to positive or negative infinity. So for example, this parabola that I drew, as x goes to positive infinity, as you go in that direction, you see how the y's get huger and huger, right? And as you go to negative infinity, the y's also get bigger and bigger. And that's called the end behavior. We'll also discuss that. This is called the end behavior of the graph. Like what happens as you go to the ends of time. So using those properties, tell me why the following graphs are not a polynomial. Like how can you tell? Like something that's from that previous stuff is broken. And which thing is it? So what's wrong with this one?
Sharp
Sure.
corner.
This has a corner at x equals what value? 0. Okay, so that's the problem. part B is a little more subtle. So, does this have any corners?
No.
No. What's wrong with it?
It does.
The domain, yeah, the domain here is -3 to infinity, assuming I meant to have a closed circle there. What's true about polynomials domains?
All numbers.
Mm-hmm. Have domain R. So the problem is that the domain is not all real numbers. And you asked about a sine wave and I gave you a cosine curve. How many of you have actually seen cosine or sine curves at some point in time in your lives before? A little bit? Okay. Did you like them?
They were fine.
They were okay? No, you didn't like them? Okay. Let's see if we can change that perception. Okay, so this is a graph of a function called cosine, which we'll discuss later in this class, like post-spring break. So assuming that this pattern continues indefinitely, what is the problem with this one? Is it continuous?
Yes.
Does it appear to have domain all real numbers?
Yes.
Mm-hmm. Okay. But the problem is if this goes forever and ever and ever, how many turning points are there?
Infinite.
So the problem is there are an infinite number of turning points. That's why this is not a polynomial.
So we just assume that's gonna keep going the same.
We assume it's going to keep going the same. Yeah, I think that's a pretty safe assumption. If you're ever confused about something like on a test, you just have to ask me or attempt to ask your TA. Like there was, like for example, in your quiz that I gave last Friday, I made a typo and asked for the domain and something, asked for the range and something when I wanted the domain as something else. So your TA just won't grade that question. You know, you read your own writing, you like see what you wish you'd written. Right? Yeah. Okay, so what we'll talk about next is how to figure out end behavior. So what happens to your polynomial as you get very, very, very large or very, very, very largely negative? So the shape of a graph with real coefficients is similar to the shape of the graph of the leading term. So the leading term is the term that is the highest degree. When you plug in huge numbers for x or huge negative numbers for x, that's the part that's going to matter the most. Everything else kind of like is chump change. So to figure out, so what we're going to do is we're going to figure out whether the function approaches either positive infinity or negative infinity. We're going to look at the highest power, and we're going to figure out what is the sign as x goes to positive or negative infinity of that term. So the first thing that I think you should do when you see a polynomial is rearrange the terms so the biggest power is first and the smallest power is last. I think the next one has that problem, right? So rearrange this so that the largest power is first and so that the smallest powers are last. Negative 2x to the 6th. Minus x to the 4th. Did you guys get the same thing when you rearranged? Negative 2x to the 6th minus x to the 4th plus 4x cubed minus x squared plus 3. Okay, so now the left end behavior and right end behavior. So think about a picture. As you go to the left, what happens to your x's? Where are they going?
Negative.
Negative. Does that make sense? So left end behavior as x goes to minus infinity. When you're plugging in really, really huge numbers, does it make sense that when you 6th power them, they're a lot bigger than when you 4th power them? So when you're plugging in humongous numbers, all that matters eventually is the biggest power. So what you have to figure out is looking at this negative 2x to the 6th. So I'll write this down. We'll say look at negative 2x to the 6th. And then think about what happens as you plug in huge negative numbers. It's not a pound sign. I don't Twitter. Or what do they call it, hashtag? Like, I really don't Twitter. Okay, so if you plug huge negative numbers into negative 2x to the sixth power first makes them positive, right? And then the negative sign makes them negative. So what we have here is as x goes to minus infinity, your polynomial p of x is going to also go to minus infinity. Okay, so for the right end behavior, I know it feels weird that you can ignore everything else. Okay, I get that, but ignore them. So if you plug in a huge negative number into the biggest power, first the sixth power takes that negative number that's huge, it makes it positive, it makes it huger by sixth powering it, right? And then it multiplies it by -2, which turns it back into a very, very, very large negative number.
Oh, so when you said left as x,
Yeah, so left end behavior means you're thinking about what happens to the picture as you look in that left direction. So looking in the left direction means your x's are going to negative infinity.
Oh, okay.
Does that make sense?
Yeah.
Okay. And for the right end behavior, that's as x goes in the other direction. So that's as x goes where? To positive infinity, not to negative infinity. Okay, and then still look at the negative 2x to the sixth. What happens when you plug in big positive numbers? So first you take that positive number and you sixth power it, which makes it even more ginormous, right? Then you multiply it by -2, which makes it ginormous but negative, right? So you also know that as x goes to infinity, p of x goes to negative infinity. So what that tells you is that your picture goes down in that direction and goes down in that direction. You don't know what happens in the middle, but you know that on the ends it goes down. The in the middle business is determined by all the other coefficients. They will determine what happens in the middle in between those points. Okay.
Why is the p of x and the x is going to be on the bottom?
Because that's the right end behavior? Wait, so what?
Different from each other, like on the top where it's left, you have it saying those two things and they're both the same to negative infinity.
Uh-huh.
On this bottom one of them says positive infinity.
That just means that when you look at the picture, some weirdness happens in the middle, but as you look to the left, it goes down forever and ever, and as you look to the right, it goes down forever and ever. It does the same thing on both sides.
Why say huge numbers? You can use any number.
You can, but left and right end behavior refer to what's happening as you go to infinity. And it's easier to think about infinity as huge numbers as opposed to like -5,
Yeah,
not a
but-
very huge number.
Yeah, but a huge number is.
The sign rules work for any number. I get
Yeah.
that. Okay, I understand that. But the point is that end behavior is behavior as you go to infinities. So I think it's easier to think about big numbers. Okay, let's look at them. So are the powers already ordered in the way they should be? Yes, okay. So think about what happens as x goes to infinity. Which one do you look at?
4x to the fifth.
4x to the fifth. So what will happen to this polynomial as x goes to infinity is the same thing that happens to just that 4x to the fifth term. So if you plug in big positive numbers, do you get out big positive numbers or big negative numbers? Big positive, does that make sense? So this will also go to infinity. How about as x goes to minus infinity? So if you plug in big negative numbers and you fifth power them, do they become positive or stay negative? Stay negative, and you multiply them by a positive 4 and they still stay negative. So that's also going to go to minus infinity. And I think I did those in the opposite order. I'm so sorry. This one, I'm not sure how Alex specifies these questions, but this is behavior. If you're going to positive infinity, you're going to the right. Negative infinity is to the left.
I was to check that some things like that. Like for the first one, I'll say find the right behavior on top of
It does that?
behavior, and then it'll flop.
It'll flop them. Okay, so just be like, I think that it will help to first like think in your head, picture right means positive infinity, left means negative. Just do that translation. I tended to do the positive infinity first. I think positives are easier than negatives. If you were to sketch a picture of this polynomial, what's going to happen is as you go in this direction, your function is going to eventually start going up. Does that make sense? And as you go in this direction, your function is going to eventually just decrease forever and ever. So what you could do to check yourself is if you find a graphing app or you have some kind of computer that has a graphing thing or a calculator, although I think that apps are easier to zoom out in and out on than a graphing calculator typically, you'll see that what happens to the picture as you plug in big positive numbers as it goes to positive infinity, big negatives it goes to negative infinity. So you can also check yourself to see if your reasoning is right. Okay. So this one, does it need to be rearranged? Okay, so who goes first?
Negative 3 x to the left.
Mm-hmm. And then plus 4x to the 9th plus 5. Okay, so as x goes to positive infinity, p of x will go to negative infinity. Does that make sense how he got that? Because the 11th power keeps it positive, right? Multiplying by negative 3 makes it negative. Was that left or right end behavior? Right. Okay. How about as x goes to minus infinity? It will go to positive infinity.
Can we write this shorter by using limits?
If you want to, sure, I can totally interpret your notation. Like, I don't have a problem with it. Yes?
I thought odd exponents give you
Odd exponents give you negative numbers. That is totally true. But you also have an odd number in front of that negative number.
So then, when p of x be going to the infinity, not negative?
For which one, left or right?
Right?
For the right. Okay, so if you plug...
Oh, wait. Okay, yeah, no.
You're good? Yep, okay. So if you were to sketch a picture of this, as your function goes to positive infinity, does your function go up or down in the end? Down, eventually. So it does some weirdness in the middle, but it goes down. How about as you go to the other side, to the left? It goes up eventually. It's not going to go right in the middle, but eventually it goes down on the right and up on the left. Okay, one more weird one. X to the 100 minus 2x to the 50 plus 1. So as x goes to positive infinity, where is your q of x going to go? Infinity as well, yep. How about as x goes to minus infinity, where is your q of x going to go?
Positive.
Also positive. So that is on the right. This is on the left. Does it make sense that when your leading coefficient has an even power, the end behavior will be the same? It'll either both be positive or both be negative?
Yeah,
Because of how signs happen?
It's determined by the first variable.
Exactly. It's determined by the evenness or oddness of that highest power, right? Okay. All right, so is that very hard?
No.
No, it's really not very hard. Okay, next we're gonna do division. And we're going to divide polynomials, like weirdness, all right? So first we're gonna review like 4th grade math. So use long division to find 123 divided by 11. Like seriously. So how do you figure out 123 over 11? What does that translate to into regular division notation with the like check mark thing? You did it that way. 11 check mark thing, 123. I don't know where I wrote 122. That makes sense? Okay, so the 11 is going into the 123. And then you think, how many 11s go into 12, right? 1. Multiply the 1 and the 11. And at this stage, what do you do to the 12 and the 11? You subtract them. And you have 13, right? And then you say, okay, well, 11's into 13, that is 1. 11, take it away, you get 2. And so your answer is 11 and 2 11ths, right? Does that make sense? Does that mean 11 times 2 11ths or 11 plus 2 11ths, technically?
Plus.
Technically, it means plus. It means 11 plus 2 11ths. So if you wanted to check your answer, you could find a common denominator, and you should get back 123 over 11. Does that make sense? Okay. So we're going to extend this process to division with polynomials. And the process is really, really similar. So just like with numbers, you have 100 spots, 10 spot, 1 spot, right? With polynomials, you have spots for the powers. So here's how we're going to do it. So we're going to divide this polynomial by 2 plus x. So it's like saying p of x over 2 plus x. Or we're having, I'm going to say, instead of 2 plus x, I'm going to say x plus 2 is going into now, when you do division with polynomials, you have to have the powers from highest power to lowest power. And it's probably also helpful to insert zeros for powers that are missing. So what is the highest power for that p of x? 2x to the 4th. Is there a third power term? Yep, it's 3x to the 3rd, right? Is there any squared term? No, so let's just say 0x squared, so we have like a placeholder for it. Is there any x term?
Yes.
Yes, minus x. And then is there any constant term?
Minus 5.
Minus 5. Okay. And now when you do division with normal numbers, you try to get the biggest, like the tens or hundreds to cancel out first, right? You start from the left and work your way to the right. Here, your goal is going to be to try to get this term to cancel. So what you think about is you think, what do you multiply this by to make it match that 2x to the 4th? So, and the 2 will matter, but it just matters in your work. You don't account for it in this step. So what do you multiply x plus x by to make it match 2x to the 4th?
2x to the 3rd.
2x to the 3rd. So that goes over this 3rd spot. And then this 2x to the 3rd multiplies by that x plus 2 and becomes 2x to the 4th plus 4x cubed. And then think about what happened in the other division steps. What do you do at this stage? You subtract. And the one tricky thing about polynomial long division is you can't forget your freaking parentheses. Okay? Does that make sense? That is the thing. Do me a favor with these parentheses. So now is it, first of all, I'll favor in a second. Is it clear that the 2x to the 4th are going to now cancel? Okay. Now, don't do this. Don't scribble out this plus and make it into a minus, because it's super confusing then as to was it a plus to start or was it a minus? I don't remember. Does that make sense? So either think to yourself, I have 3x to the third minus 4x to the third, or put the new sign in a circle above the old sign. Okay, it will help you not make mistakes. I know it's one more writing stage. So then now you subtract. What is 3x to the third minus 4x to the third? Negative x to the third. And the other things just carry down. Plus 0x squared minus x minus 5.
You bring all of them down, not just the next one.
You can just bring the next one down, you can bring all of them down. It depends on the context as to which ones have to come down. So you could just keep track of which ones you need. Like there are ways to write less. For now, I'm just gonna bring them all down, okay? Just first time through. Now, same stage, repeat. Think about what do you multiply this x by to make it match that negative x to the third. So when they subtract, they cancel. So what would it be? Minus x squared, yep. So that becomes minus x cubed minus 2x squared, and you take it away. If you're doing your homework and you get weirdness, you probably made a sign error. Does that make sense? That's the most common thing that's going to happen here. So what is x to the third minus a negative x to the third?
Nothing.
No x thirds. And how about 0x squared minus a negative 2x squared? Positive 2x squared. Minus x minus 5 carry down. Okay, then you think, what do you multiply x by to make it match 2x squared? 2x. So 2x squared plus 4x. Take it away. Okay, what's negative x minus 4x going to be? We're almost done. What do you multiply x by to make it match negative 5x? Minus 5. So minus 5x minus 10. Take away. What's your remainder? Plus 5. Okay, so that process is long, and as a result, I'm not going to ask you to do very many of them, or it would have been better if I would have decreased the power and not made it fourth. Does that make sense? Now, you stop with numbers when your remainder is less than the thing you're dividing by, right? With polynomials, you stop when the degree of this is degree 0 technically, is less than the degree of the thing you're dividing by. Okay, so it's kind of like, instead of it being referring to sizes and quantities, then this system is degrees. That's okay. And if you were to rewrite p of x over x plus 2, it'd be your quotient, which was x cubed plus, is this right, x squared? Actually, I made a mistake in my notes. I don't know if it's right anymore. I totally boo-booed. I boo-booed twice. Oh my goodness, this is embarrassing. Okay, erase that. That's wrong. Okay, so this will be 2x to the third minus x squared plus 2x minus 5. And then plus your remainder, which is what over what?
5 over x plus 2.
5 over x plus 2. So if you had infinite time and infinite patience and had nothing else better to do, how could you check your answer?
You could plug in numbers.
Sure, that would check it for specific things. What I was thinking is you could get think about this whole thing as being over 1 and multiply it by x plus 2 over x plus 2, and that should give you back what you had in the beginning. You could get a common denominator. Okay, let's try another one. It's a little bit shorter. Okay, 6x squared minus 30 plus 9x cubed by x minus 2. Okay, so that's like saying 6x squared minus 30 plus 9x cubed over x minus 2. Before I translate that into division, do you have to rearrange the powers? Yes. So x minus 2 is going into 9x cubed plus 6x squared. I'm going to put in a 0x, and then last is minus 30. Okay, and then you think, what do you multiply x by to make it match 9x cubed? 9x squared. So 9x cubed minus 18x squared. Parenthesis, take away. So watch the negative signs. What is 6 minus negative 18? 24. It kind of helps talk to yourself a little bit. If I take away a negative, makes positive, right? All right, and then think, what do you multiply x by to make it match 24x squared? 24x. So 24x squared minus 48x. Take it away. So the 24x squareds cancel. What is 0 minus negative 48x? Positive 48x, right? And if you line your spaces up, things up, like you put your x squares over your x squares and your x's over your x's, you can tell you're going to stop when you're on that constant term. It's your last one. So what do you multiply x by to make it match 48x? 48. So 48x minus, I think that's 96. Take it away. And your remainder is 66. So your answer is 9x squared plus 24x plus 48 plus 66 over x minus 2. I am pretty sure that's how Alex wants it, because I was actually looking at the questions as I made your note sheet.
Also, the answer to the question 4 is everything that was underneath here plus what was 5.
Yeah, think about what the one we did where you did 123 and we divided in 11, right? We got that was equal to, what was it, 11 and 2 over 11, right?
Yeah.
Which is the same thing as 11 plus 2 11s, right?
Yeah.
So this 11 was that number, right? See what I mean? That's the quotient. And then there's the remainder over the divisor. Okay. How about you give this one a try? Because there's a bunch of zeros in it. It actually works out nicely. You should get a remainder of 0. So give it a shot. Who goes inside the check mark? The one on top. Okay, so start that. Give it a try. You guys get the same thing? A squared minus 3a plus 9. So that division just equals a squared minus 3a plus 9. There's no remainder. Does that look a little bit familiar? Check this out. If this is true, like if these two things are equal, doesn't it mean that a cubed plus 27 equals a plus 3 times a squared minus 3a plus 9? That's that sum, or that's the sum of cubes factor formula. Yeah, okay. So, okay. Have any of you in high school learned this technique called synthetic division? Okay, you can use it to check your answers, but it's not very useful because it doesn't generalize. So what that means, if you know it, I'm just going to give you my spiel as to why I'm not going to teach it. It only works if you're dividing by a x plus or minus a number. It doesn't work for other stuff. So if you know that trick, great. You can use it for some stuff, but this technique works for all sorts of things. I also think it parallels actual division more, so it's easier to remember. Does that make sense a little bit? Okay. So this example is one, if you know synthetic division, where it will not work unless you're really clever about it. So if you don't know what synthetic division is, don't worry about it. It's not important. So we're going to divide 3x plus 2 into 12x squared plus 11x minus 2. A little bit of rearranging, but at least no zero placeholders. Okay, so first part is, what do you multiply 3x by to make it match 12x squared? 4x. So that's 12x squared plus 8x. Take it away. 3x minus 2. So what do you multiply 3x by to make it match 3x? 1. So 3x plus 2. And do those 2's cancel? No, they are negative 4. So your answer is 4x plus 1 plus negative 4 over 3x plus 2. You could also say minus, and that wouldn't be a problem. Does that make sense? Instead of plus and negative, you could just say subtraction. Okay.
If we were to write like 4x plus 1 for the main there, would that be wrong?
No, but I'm not sure that's the form that Alex is looking for.
I mean, like on a quiz or something.
Oh God, I'm going to specify this. I think I'd prefer that you write it like this, because when you use these problems in the context of a calculus class, you have to like use it like that. Does that make sense? But I'll specify as to give you a remainder as a fraction or something to try to like make it clear how I want to have the answer. It's a good question though. Okay. How is this next one different than the previous ones?
Quotient is raised by power.
The
Divisor.
The divisor is not just x. Does that make sense? So this question is taken from a Calculus 2 textbook that I used, because they have to do a problem and it involves this division. So your textbook does not actually have anything like this, but it's a good idea to know how to do it. X to the fifth plus 0x to the fourth, 0x cubed, 0x squared plus x minus 1. This will actually be a really short one because the power on the 3 is awfully close to the power of the 5. But the process is the same. You think, what do you multiply x cubed by to make it match x to the fifth?
Squared.
X squared is correct, yep. So I'm going to put that over the x squared spot. And I get x to the fifth plus x squared. Do you see what I did there? Tyler doesn't like it. Does that make sense, though? I just put the x squared, because x squared times x cubed is x to the fifth, right? And so the zeros don't actually matter unless they end up showing up. So you've got 0 minus 0, the fourth's already gone. Does that make sense? you've got 0 minus 0, the third is gone. All you now have is negative x squared plus x minus 1. And remember how I said you stop whenever the degree of this is less than the thing you're dividing by? That's actually your remainder. So this division gives you x squared plus negative x squared plus x minus 1 all over x cubed plus 1. That is the result of that division. So in your remainder term, the degree of the numerator should be less than the degree of the denominator. That's when you know to stop. The next one's also taken from my calc textbook. So set up the division. It's going to exactly one step. So try it, okay? And it was weird, just give it a shot. So what's the one number you multiply by?
3.
3. And for your remainder, did you get negative 3x minus 4? So the result of this division is 3 plus negative 3x minus 4 over x squared plus 3x plus 2. If you were in like a calculus 2 class, you've got to do some more stuff with that, but that's the first step, is knowing how to do the division. Okay. All right. Last question. We might only get to do one of them, but that's okay, I think. Without graphing, state the left and right end behavior, the maximum number of x-intercepts, and the maximum number of local extrema. So I need to explain what local extrema is. We'll get to that last. So first, the left and right end behavior. So left behavior is as x goes to positive infinity or negative infinity? Negative infinity. Are these powers already arranged so that the highest power is first? Mm-hmm. So you look at the x cubed and you think, okay, as I plug in huge negative numbers, do I get a positive negative for negative number? Negative number. How about right end behavior? X goes to, and your polynomial will also go to infinity. Okay, the maximum number of x-intercepts. Say that again? You're thinking of turnaround points. So think about, so you know parabolas, right? Parabolas have at most how many intercepts? At most 2. Does that make sense? So if the green parabola was 2, across the x-axis at most twice, right? So in this case, the maximum number of x-intercepts is going to be 3. It's the same as the degree. There could be less, but it will be that many at most. Now the maximum, now local extrema, that means that your picture has like a lowest point or a highest point. So think about a parabola. Parabolas have how many lowest or highest points? They have 1, right? So parabola has degree 2, and it has 1 little max or min point. A line has degree 1, it has no max min points, right? So the number of local extrema is 1 less. In this case, it'll be 2. It's always 1 less, yep. And this is also a maximum number. There could be less than 2, but that is the most it will be. It's kind of like they call it an upper bound. So just do that part for part B, okay? It'll take like 2 seconds, maybe 10 if you got it really slow. So what is the maximum number of x-intercepts here? 4. And what is the maximum number of local extrema?
3.
Is 3. And that doesn't mean that there are exactly 4 intercepts or exactly 3 extrema. It means that that's the most there could be. It's like if you go out and you find 3, you know that there can't be any more.